Okay, so what does mean Dirac operator here? So maybe most of you know the Schrodinger equation. So you have E dt plus Laplacian minus the potential V acts on a function psi of x. So this is 0. So t is the time and x is the position. So this is just a function, okay, that goes from, so psi goes from R3 in the complex plane. Then this is the Schrodinger equation. Here, delta is Laplacian, so minus delta is just x squared d1 So if we are here in RD, for example, here we are in R3, let's put 3 here, okay. This, okay, so this is the Laplacian, so we take second partial derivative. So this equation describes the motion of quantum particle, non-relativistic quantum particle. Okay, so here I forgot the Planck constant and so on, the mass, blah, blah, blah. So I'm taking all this, I mean, is equal to 1. And you have, so this is quantum mechanic, okay. And you have the special relativity. So in particular, you have in special relativity, you have this Pythagorean relation. So p squared plus m squared c4. Okay, so E is the energy. C here is speed of light. And P here is the momentum. M is the mass of the particle, okay? So here you have quantum mechanic versus special relativity. All right, so now the story starts with these two guys. In fact, once Schrodinger found the equation. Well, I don't have time to show you how to find the Schrodinger equation, but I will show you how to find the Dirac equation. So, and the question was how to combine, how to unify these two notions. Okay, so you have notion of quantum mechanics and you have notion of special relativity. Okay, so let me just recall you what happens in quantum mechanics. So in quantum mechanics, you have what we call quantization, okay? So in fact, the energy, quantify the energy with E h bar dt, okay? And the momentum, you have a quantification main h bar of the gradient, okay? So this is the gradient in R3, of course, okay? And here, this is the Planck constant. Okay, so the question at that time is how to unify these two notions. And in fact, there have been very quickly an answer for this question. I mean, an answer which is naive. Somehow you just replace, I mean, E by this and the momentum by its quantization, okay? So let's take C is equal to 1 is equal to the h bar and so on. Okay, so then you will have the following. So you will have E dt of function is equal to minus Laplacian plus m squared applied to the function psi. Okay, and you get this this equation. So at that moment, of course, we didn't know how to define this monster, okay? But nowadays we know how to do it. But this equation, I mean, it has a big problem, okay? So because in quantum mechanics, we always, I mean, write equation in the following way. So we have EDT of function psi is equal to h of phi, okay? I mean, the equation in quantum mechanics writes like this, at least in the linearized, I mean, setting. So here, I mean, h would be, I mean, linear and local operator, okay? And here you have just one derivative, because what is behind this, the fact, if you have such system, okay, and you say that, for example, at t is equal to 0, okay, t is equal to 0, so x, this is, I mean, your initial data, and somehow, I mean, it would be more easy when you have dt like this, and your solution would be just exponential, I mean, et of h of the datum at t equal to 0. So the solution are of this form, okay? So the problem here, if you square these guys, okay, so how to get a linear operator, so you will end up with dt square of psi is equal minus Laplacian m square of psi. So, and here you have second derivative. Okay, so this is what we call, in fact, Klein-Gordon here or here, and it's the same. This is the Klein-Gordon equation. Okay, so the Klein-Gordon, as I said, nowadays we can give, I mean, meaning and go and sit in that where, I mean, this equation just, I mean, fits is quantum field theory, okay? And in fact, this, I mean, governs or describes the motion of a spinless particle, okay? Spinless particle. But we don't want this. We don't want to describe the motion of particles which have been, which has, I mean, speed close to the speed of light. So, and then you have these guys. So Paul Dirac, that, I mean, I guess everybody know who is. Okay, so the idea of Paul Dirac is to find that equation in the following way. So he said that, okay, I must look for something like that, for example. So I'm putting h here. Well, let's forget h bar. So I'm putting alpha 1 dx1 plus alpha 2 dx2, alpha 3 dx3. I mean, we have all the derivative here, okay, of psi plus m beta of psi, okay? And I need to look for these unknowns. I mean, you have here the alphas and betas. We need to look for these quantities. Somehow, when you take the square of this expression, you will get minus Laplacian plus m squared. Okay. Now, just let's give some example. Or just remark. So imagine you are in R2, okay? So how can you factorize, I mean, the Laplacian? So minus, let's say, Laplacian. So the x1 square. Okay, so this is just equal, you can write it that dx1 plus e dx2 times dx1 minus e dx2. Okay, this is the Cauchy-Riemann operator. However, you have problem here because somehow we need, in quantum mechanics, we need, say, a symmetric operator. And clearly you see that this guy is not symmetric. Okay, this is not the adjoint or the symmetry of this operator, okay? In fact, we say A star here. So this is not good for us, okay? Now, however, if you pass to matrices, if you allow, for example, alpha 1, alpha 2 to be matrices, then you can do this as follow. So you say Laplacian, you just pick this matrix, say sigma 1 dx1 plus sigma 2 dx2, where sigma 1 is just 1, 0, 1, and sigma 2 is I minus I, 0. And if you plug here these two matrices, and of course here now you have a two-dimensional Laplacian, so you have the matrix Laplacian. If you pick the square, then you will get minus then you will get Laplacian in this case. Okay. Now the problem is that, be careful, we still have the mass. For example, if we are in 2 dimensions, we can add the mass, and in this case, for example, we can take m sigma 3, and here sigma 3 is just 1, 0, 0, minus 1. And again, in this situation, the square of these guys is equal to Laplacian plus m square, okay? Or minus m square. Wait, what? Let's put minus e in front of this matrices. So we will have minus Laplacian plus m square times identity 2 here, okay? Now, in R3, for example, if you do something, I mean, this is an algebra. I mean, this is what we call Pauli algebra. Okay, and let me just recall the property here. In fact, you can see that sigma g, sigma k plus sigma k, sigma g is equal to 2 times delta gk. And you have the sigma g square is equal to the identity. That's okay. And here, in fact, you achieve, I mean, the algebra. That's maximal, okay? You cannot, I mean, add another matrix, okay? So in R3, if you try to do the same thing, I mean, you see here, I mean, we have 3 matrices. I mean, it's full. We cannot add another matrices for the third derivative, for example. So the only thing that you can do is to take 4 by 4 matrices. I mean, you can check this. And in fact, that's what Dirac did. In fact, he defined alpha G to be the following matrices. They are formed by the Pauli matrices. So we put Pauli matrices in anti-diagonal. And sigma 3 here, the analogous of sigma 3 would be the beta that I'm denoting by. So E2, 0, 0, minus E2. Okay. Dirac matrices. So in the end, we have got the following. Say we have E dt of psi is equal to minus E, the sum over G from 1 to 3, alpha J dxj plus m beta, okay? Applied to psi. And the square of these guys gives you minus Laplacian plus m square E4, okay? And similarly to the Pauli matrices, I mean, because of this relation, you have the same, I mean, property for the Dirac matrices. So alpha G, alpha K plus alpha K, alpha G, K. And here you have the identity. And also, I mean, you have also alpha J beta plus beta alpha J is equal to 0. And beta square is equal to the identity. Okay, so in the end, Dirac, managed, to solve the problem, and he found this expression here. And the good thing here now, if we denote this by dm for Dirac, okay, then dm is what we call minus e. Let me use this notation, alpha grad plus m beta, okay? And this means that minus, we take the sum from 1 to 3, alpha j, dxj plus m beta, okay? And here we do this, whenever we have, for example, a vector in R3, then this means that alpha j, xj, okay? All right, so we have this, what we call a Dirac operator. And as I said, the good thing that is dm is a local version now. Of this square root minus Laplacian m square e4. Okay, but the problem is that here we had to pay something, and now the wave function now, this wave, if x takes value from R3, and it is a vector, complex vector, okay, with 4 components, because we have this 4x4 matrices. Okay, so this is if we try, we can write this Dirac operator. So dm, we can write it in this matrix form. So we will have here minus sigma dot grad. Here we'll have the identity minus m identity, and again here sigma dot. Okay. In fact, if you take the Fourier transform, for example, take the Fourier dm Fourier minus 1, then this gives you, or just take Fourier, okay? If you apply Fourier, then you will have m identity, and here you will have sigma xc for the Fourier variable, and minus m1. And the square of these guys, if you take the square, then in fact you get xc square plus m square, okay, e4. And now you can easily see that in fact this is a unitary, the Dirac operator is unitarily equivalent to multiplication by this factor, okay? And this, by definition of first order Sobolev space, that I'm going to recall here. So what I note, H1 R3 value C4. In the following, I will just denote it by H1 of R3, like this. So those are, subset of L2 of R3, such that the first derivative is in L2. First derivative in sense of distribution, okay? And you see, in fact, since we are in R3, in fact, this means when you have a function here in this space, okay, that means that c squared plus 1 or m or constant, put something different from 0, okay, is finite, okay? This is equivalent to be in H1 of R3. And here, since we have a vector valued function, so you need to work with vectors. Okay. Then with this, in fact, we see that the Dirac operator defined on the domain which is H1, is in fact self-adjoint, okay? And moreover, the spectrum of this operator is given by the union of this two interval minus infinity minus m, union m plus infinity. Okay, you see it from this. So when you have a multiplication operator like this, and you have such unitary equivalence, in fact, the spectrum is just here. Be careful. Here we took the square here. Okay, so that means that this matrix has two eigenvalues. Okay, say lambda 1 of xi, which is equal to square root xi squared plus m squared, which is equal to minus lambda 2 of xi. Okay, and both are of multiplicity 2. Okay. So when you take the range of this function of this eigenvalue, then this gives you, I mean, the spectrum. So we see with plus, you will get this interval, and with minus, you will get this interval. Okay. And this is one of the amazing thing in the Dirac equation. Okay. So this means that, I mean, your operator is not semi-bounded. Okay. So dm is not bigger than, say, constant phi in the sense of, if you take the scalar product. Okay. And at that moment, I mean, Dirac, I mean, point out the fact that we have, in fact, somehow negative energy. And this is with one of the, I mean, most important things that comes out from this Dirac equation. Okay, so I would stop here for this first part. So those are, I mean, somehow just an introduction, several definitions that I need before, I mean, going to the next part.